Welcome back to the deep dive. So we're shifting gears a little bit today.
Yeah, a new format.
A new format. Usually we look at, the results of technology, how it changes society, the market impact.
Right, the big picture stuff.
But today we are taking a strictly engineering perspective. We're launching what we're calling the Practical AI Digest.
I love this. So we're going to take one specific architecture, just one, strip away all the marketing hype, and explain exactly how it works so you can actually understand the mechanism under the hood.
Exactly. And the topic for today is something that I think a lot of people feel they understand on a surface level, but the actual mechanics are quite surprising.
Yeah.
We are looking at the engine behind the massive, massive explosion in AI art we've seen over the last couple of years. We're talking about latent diffusion models, LDMs.
This is the thing that powers Stable Diffusion. Is basically the reason you can now generate these incredible high-fidelity images on a home computer.
Instead of needing a giant server farm. And that is the key hook here. I mean, everyone has seen the output. Midjourney, Delhi, Stable Diffusion.
Oh, yeah.
You type a cyberpunk city in the style of Van Gogh, and boom, 5 seconds later, you have a masterpiece. But very few people ask the next question.
Which is?
What is the engine driving this?
Yeah.
And specifically, how did we get from models that needed, like you said, a supercomputer to something that can run on a gaming laptop?
And that's the core conflict, the problem we need to address. Before this paper, the high-resolution image synthesis with latent diffusion models paper, this whole field was incredibly expensive.
It was a rich man's game.
Totally.
Let's put a number on expensive, because I think people just assume AI lives in the cloud and it's basically free.
Oh, it's so far from free.
Yeah.
I mean, if you look at the source material, they highlight that training one of these powerful pixel-based diffusion models, it took hundreds of GPU days.
Hundreds?
Yeah, they cite examples from like 150 up to 1,000 V100 days.
Okay, let's just clarify that for you listening. A V100 is a top-tier enterprise-grade graphics card. So 1,000 V100 days means if you had one of these very expensive cards, it would take you almost 3 years to train the model.
Once.
Just once.
Exactly. And that's just the training part. The inference, so actually making an image after you type a prompt, that was also painfully slow.
Why?
Because the neural network had to sequentially evaluate a massive, massive amount of data.
So the mission of this deep dive is to unpack the architecture that solved this bottleneck. We're not just making images, we are, I guess, making them efficiently. We're going to break down the latent part of latent diffusion models.
It's what democratized high-resolution image generation. And the whole trick, the core idea, was separating the compression phase from the generative phase.
Okay, so let's get into that. Section 1, the intuition and the problem with pixels. So before we can understand why latent diffusion is so special, we need to understand what standard diffusion even is.
Right, the baseline.
If I'm a developer looking at this for the first time, what's the basic mechanism?
The basic idea is something called iterative denoising. It's, you can think of it as a model that's designed to learn a data distribution.
By
Gradually removing noise. It's a two-way street.
You have the forward process and the reverse process.
Right. So the forward process is fixed. It's easy. You take a clean image, let's say a photo of a cat, and you just gradually add Gaussian noise to it.
A little bit at a time.
Step by step. So, step 1, it's a little grainy. Step 50, it's very grainy. By step 1,000, it's just pure static. The image is completely gone.
Okay, that seems simple enough. Ruining a photo is easy.
It is. The magic is the reverse process. This is where you train a neural network to look at that pure static and predict the noise that was added at the previous step.
Ah, so it's learning to go backwards.
Exactly. Because if you can predict the noise, you can subtract it.
Yeah.
And if you do that over and over, step by step, backwards from total randomness, you eventually reveal a clear image.
So the model is kind of like a professional art restorer. It's looking at this messy, noisy signal and saying, okay, I know what part of this is just static and what part is actual structure.
And it just wipes the static away. That's a perfect way to put it.
And ideally, you end up with a beautiful, high-fidelity image.
You do.
Yeah.
But here's the problem, and it's a huge problem. With standard models, like DALL-E 2 or the original guided diffusion models, they do all of this in pixel space.
Meaning it's literally calculating every single pixel.
Every single pixel. Think about it. You have a 1024 by 1024 image. That's over 1 million pixels.
And each one has 3 color channels.
Red, green, and blue.
Okay.
So it's more like 3 million data points. And the model has to process that entire massive grid for every single step of the denoising.
Every step, which can be hundreds or thousands of steps. Okay, I see it now.
And this is where we hit what the paper calls the pixel space bottleneck.
Right.
And this right here is probably the most critical conceptual takeaway from this whole thing. Digital images contain a massive amount of information, right? But not all of that information is actually important. Semantically important.
What do you mean by semantically important?
Okay, well, imagine a photo of a brick wall. The semantic information is, this is a brick wall, it's red, the mortar is gray.
The concept.
The concept, exactly. Yeah. But the actual digital image also contains all this high-frequency detail.
High-frequency meaning like the microscopic grain on the brick.
Yes. Imperceptible noise. Tiny, tiny shifts in the gradient of a shadow on one single brick. The exact texture of the mortar if you zoomed in 1,000 times. All these little details take up a huge amount of data to encode.
But do they matter to me as the person looking at the picture?
Not really. I mean, if I showed you a picture of that wall and then I showed you another one where I just slightly blurred the texture or shifted the noise pattern, you still just say, that's a brick wall.
Right. The wallness of it hasn't changed.
Exactly. But the standard diffusion models, they don't know that.
They can't tell the difference between the concept and the tiny details.
No, because they're what are called likelihood-based models. Mathematically, they're obligated to model everything. So they spend a completely disproportionate amount of their compute power modeling these imperceptible high-frequency details.
So it's like trying to write a book summary by, I don't know, analyzing the microscopic fibers of the paper on every single page.
Instead of just reading the plot.
Instead of just reading the plot points.
Yeah, that is the perfect analogy. You are burning these incredibly expensive GPU cycles just to figure out the texture of the paper, when all you really want is the story. That's the difference between perceptual compression and semantic compression.
So the goal of the latent diffusion model is to stop looking at the paper fibers.
Yes. The goal is to find a representation of the image, a different space, that is computationally way, way cheaper, but is perceptually equivalent to the original.
We want to find a space where we can do the heavy lifting of generation without being bogged down by millions of useless pixels.
Precisely.
Okay, this brings us to section 2, the system architecture. The paper splits this whole system into 2 very distinct phases. And phase 1, you said, is strictly about compression.
Right. First, we need to get out of pixel space. And to do that, they introduce a component called an autoencoder.
Okay, for the engineers listening, let's break down the specs of this autoencoder.
So an autoencoder has 2 parts. They have an encoder, which we can call encoder, which we'll call decoder.
Encoder and decoder.
The encoder takes your high-dimensional image, 6 LRs, that's your massive grid of RGB pixels, and it crunches it down into something called a latent representation. We call that decoder.
So $6 is the big original image, and ZDOL is the tiny compressed version.
Correct. And ZLDA lives in what we call latent space. It's a much, much lower dimensional space. The paper talks about a specific parameter for this, a downsampling factor, which they call fill down.
And what does that control?
It just controls the ratio of compression.
Yeah.
So if fill dollars is equal to 4, the latent representations has a height and width that's a quarter of the original image.
And if $5 is 8, it's 1/8.
Yep.
So we're shrinking the map. But, I mean, that brings me back to my earlier concern. When you shrink an image, you lose quality. If I take a big photo in Photoshop and I shrink it down to 10% and then try to blow it back up, it looks awful. It's all pixelated and blurry. How does the LDM avoid that?
This is such a critical design choice in the paper. They don't just use a standard loss function, like an L1 or L2 loss.
Mean squared error, things like that.
Right. Those standard loss functions tend to produce really blurry results because the model is trying to average out all the uncertainty.
Right. The mean of all possible sharp edges ends up being just a blurry gradient.
Exactly. So to keep things sharp, they do something clever. They use a perceptual loss combined with a patch-based adversarial objective.
Okay, that sounds like we're in Jan territory.
It's borrowed directly from Jan's generative adversarial networks. They essentially have a second network, a discriminator, that looks at the reconstructed image that comes out of the decoder.
And it critiques it.
It critiques it. It basically asks, does this little patch of the image look like a real texture? Is this sharp? Or is this blurry mush?
So it forces the autoencoder to be honest. It can't just get away with a blurry approximation.
No, it has to maintain what they call local realism.
Local realism. I like that.
And that's what ensures that even though Siller is highly compressed, when you run it back through the decoder dollar, the output image looks crisp and detailed.
Now, there's a technical nuance here about regularization. The paper mentions 2 ways to keep this latent space well-behaved. Why do we care if the latent space is well-behaved?
Well, imagine if you just mapped a bunch of images to a latent space, and the points were just scattered completely randomly.
So a cat is here, and a millimeter away is a toaster.
In between is just garbage static.
Yeah.
That would be a high-variance, chaotic space.
You can't navigate that.
You can't. And you certainly can't train a diffusion model on it. Diffusion models need a smooth, continuous space that they can walk through. So regularization is about forcing the latent vectors to follow a standard, predictable distribution.
And what are the 2 options they talk about?
Option A is called KL regularization. This adds a slight penalty that kind of nudges the latent distribution towards a standard normal distribution. It's very similar to how variational autoencoders, or VAEs, work.
Okay, and option B?
Option B is VQ regularization, which stands for vector quantization. This uses a kind of code book of learned vectors. It quantizes the latent space into discrete, separate steps. This is more like what you see in VQGANs.
So which one do they end up going with?
They experimented with both, but the KL regularization version is what became the standard for stable diffusion. It just offers a really nice balance of quality and stability.
Okay, so let's just recap phase 1. We take an image, we use an encoder to crunch it down into a tiny, efficient latent vector subset. We then use a decoder to prove that we can turn Ziegler's back into a sharp-looking image. But we haven't generated anything new yet.
Not a thing. We're just compressing and decompressing.
Just building the stage.
Exactly. Phase 2 is where the performance actually happens. This is latent diffusion.
This is the core shift. We are no longer diffusing pixels. We are diffusing the latent vectors.
Right. We take that compressed representation, Civadiaus, we add noise to that, and then we train a model to remove the noise from Ziller.
So we are essentially hallucinating the compressed concept of an image rather than the image itself.
That's a great way to put it. And because ZZs is so much smaller than the original image 6Zs, the computational cost just drops off a cliff.
Okay, let's talk about the backbone. What's the neural network that's actually doing this work? Is it a transformer? It feels like everything is a transformer these days.
Right, that's the default assumption.
DLE1 used a transformer.
It did. But no, and this is a really specific and I think very smart engineering decision. They use a time-conditional UNet.
A UNet? Why a UNet?
So, the paper argues that transformers are naturally sequence-based. They treat data like a stream of words in a sentence.
One after another.
But images, even latent images, they aren't sequences. They're 2D spatial grids. They have structure.
The top left corner is related to the top right corner in a way that the first word of a sentence isn't necessarily related to the last.
Exactly. A UNet is built from convolutional layers, and convolutions are designed specifically to process spatial grids. They have what's called an inductive bias towards images. They naturally understand things like locality and, translation and variance.
So by using a UNet, they're working with the structure of the data, not trying to force it into a different shape.
Yeah.
And I assume this is faster.
Oh, much faster. Remember our downsampling factor? $5.
Yep.
If $5 is 8, the latent space has 64 times fewer data points than the original pixel space. So the UNet is processing a tiny, tiny fraction of the data that a standard diffusion model would have to.
And that explains how we can run this on a single consumer GPU.
That's the whole ball game. This design allows for training on limited resources and, crucially, very efficient inference.
Let's look at the math for just a second. We don't need to get bogged down, but for the engineers trying to implement this, what's the objective function? What is the model actually trying to minimize?
It's a simplified version of the standard diffusion loss. The formula is the LLDM equals the expectation of the squared difference between epsilon and epsilon theta.
Okay, let's translate that into plain English.
For sure.
Yeah.
You have the actual noise, that's epsilon, which you just sampled from a normal distribution.
Okay.
And you have the predicted noise, that's epsilon theta, which comes from your neural network, the UNet.
Right.
The UNet looks at the noisy latent vector, $z, at a specific time step, $t, and it makes a prediction. The objective is simply to make the predicted noise as close as possible to the actual noise.
So the model is just playing a guessing game. It's saying, I see this messy static. I think the noise you added looks like this specific pattern.
And we grade it on how close its guess was.
If it guesses the noise correctly, we can subtract it and take one step closer to a clean image.
That's it.
So now we have a system that can generate random images from noise, and it can do it really efficiently. But we don't want random images.
No.
We want specific images. We want a cat eating pizza.
Right. And this brings us to section 4, conditioning. This is the mechanism that enables text-to-image generation.
how do we tell the model what to generate? I mean, the UNet speaks this spatial image language, but our prompts are in language sequence language. We need a bridge between the two.
You do. And the solution they implemented is brilliant. It's called cross-attention.
This is a mechanism that's borrowed from the transformer world, isn't it?
It is, yeah. They effectively graft these cross-attention layers onto the UNet backbone. But they make the really smart architectural move here. They separate the text processing from the image generation. They introduce what they call a domain-specific encoder, which they label as tau theta. It's a totally separate model. It could be BERT, it could be a clique model, that takes your input, say your text prompt,
Right.
and it projects it into an intermediate representation.
So the text goes into its own dedicated processor first before it ever touches the image generator.
Yes. And only then is that processed text representation fed into the UNet through the attention mechanism. If you think of the attention formula, attention of Q, K, V.
Query, key, and value.
Right. Let's map those terms to this system.
Okay, who's the query?
The query comes from the UNet. It's coming from the intermediate layers of the image in progress. You can think of it as the image asking questions.
And the keys and values.
The keys and values come from our conditioning input, so the text prompt after it's been processed by that tau theta encoder.
So visually, can you walk me through what's happening here?
Okay, imagine the UNet is trying to denoise a little patch of the latent image. It generates a query that is effectively asking what is supposed to be in this top left corner right now.
Okay.
The cross-attention layer then takes that query and compares it to the keys from the text prompt. If the prompt is a red cat on a blue table, the keys for red and cat might light up for that area.
They become relevant.
They become relevant. And then the values provide the actual information.
Sure.
This area should have red, furry texture.
That's a fantastic explanation. So the image generation process is literally querying the text prompt for guidance at every single step of the denoising.
And this design is so incredibly flexible. Because the UNet only interacts with the conditioning through this clean cross-attention interface, the conditioning input can be anything.
Doesn't have to be text.
Nope. As long as you have a domain-specific encoder, a tau theta, that can turn your input into the right shape for the key and value pairs.
You can plug anything in.
You can condition on anything. You can use semantic maps, so like a color-coded layout. You can condition on class labels or even other images.
Ah, and this explains why the whole Stable Diffusion ecosystem is so modular. People are constantly swapping out these conditioning encoders to build things like ControlNet or IP adapter.
Without having to retrain the core UNet from scratch.
It's a plug-and-play architecture for control signals.
Exactly.
Okay, so we've covered the autoencoder, the latent diffusion process itself, and the conditioning. Now let's get practical. Section 5, trade-offs and tuning. If I'm an engineer trying to implement this, or even just a power user trying to optimize my workflow, what are the levers I need to know about? The paper spends a lot of time on that downsampling factor, $5.
Yes, this is the sweet spot analysis. They tested a whole range of factors. And five of 1, 2, 4, 8, 16, all the way up to 32.
And just to remind everyone, $5 is how much we compress the image.
Right.
So let's look at the extremes. What happens at $302? That's a massive amount of compression.
It is. At feet 302 hours, you're squashing a 256 by 256 image all the way down to an 8 by 8 grid. It's tiny.
And the benefit is speed, I assume?
The benefit is the diffusion model is lightning fast. It has almost no data to process. But the downside is the autoencoder just fails. It abstracts away way too much information.
The map becomes too simple to be useful.
Exactly. The perceptual quality just stagnates. You lose all the texture, you lose text legibility. The reconstruction looks, I don't know, sketchy because the latent space just doesn't have the capacity to store the fine details anymore.
Okay, and what about the other extreme? And 4 of 1 or 2?
Well, 4111 is just pixel space. You're right back to the original problem.
So it's slow, high memory usage.
You're not gaining any of the efficiency benefits that make the LDM architecture so great.
So what's the verdict? Where's the Goldilocks zone?
So the paper concludes that the optimal balance is somewhere between a 5 of 4 and a 5 of 8. This is where they achieved the best FID scores.
And FI.
First at inception distance. It's basically the standard metric for measuring how real generated images look compared to a data set of real images. Lower is better.
Okay.
And the models they call LDM4 and LDM8, downsampling by 4 and 8, they achieve state-of-the-art results on datasets like CelebHQ and ImageNet.
And they were faster.
They significantly outperformed the pixel-based models in sample throughput, which is speed, while also getting lower FID scores, which is better quality.
It is so rare in engineering to get faster and better at the same time. Usually you have to pick one.
It's very rare, and that's really why this paper was such a breakthrough. But there's another practical feature that I think is even cooler.
Oh,
It's called convolutional sampling.
and what does that enable?
It enables resolution independence. Most transformer-based models are totally stuck generating images at the exact resolution they were trained on.
Right. If you trained on 256 by 256, you get 256 by 256.
That's it. But LDMs are different. Because the model is fully convolutional, it learns features rather than fixed positions. It learns what a tree looks like or what sky looks like,
Okay.
which means you can take a model that was trained on 256 by 256 images and just apply it to a 1024 by 424 canvas.
Yeah, it doesn't just break.
It doesn't break, it just generates more stuff. If you ask for a landscape, it'll just generate a wider landscape with more trees and more mountains. The paper shows these amazing examples of generating huge, consistent panoramas that are way larger than any of the training images.
That is huge for creative applications. It implies the model understands textures and relationships on a local level, so it can just tile them indefinitely.
It also enables these really powerful editing workflows, like in-painting.
So filling in a missing part of an image.
Exactly. You can mask out a part of an image and just ask the model to fill it in.
Mm-hmm.
The LDM handles this completely naturally. It just treats the unmasked part as known latent codes and then diffuses the masked part to match the context.
How does it stack up against specialized tools built just for that?
So the paper compares it against specialized in-painting architectures, like a model called Llama, and the LDM achieves competitive performance.
Which is pretty remarkable for a general-purpose model.
It's amazing. It wasn't built just for in-painting, but it happens to be great at repair work, too.
And what about super resolution? Upscaling.
Same story. You can use LDMs to upscale low-res images. And because they're likelihood-based, they avoid something called mode collapse.
That's a classic Jan problem, right? Where the model just learns to output the same generic, good-looking face over and over again.
Exactly. LDMs preserve diversity. And unlike the big autoaggressive models, they don't need billions and billions of parameters to do it. They're just efficient, diverse, and sharp.
So if we step back and look at the big picture here, the LDM architecture really is a kind of best of all worlds approach.
I think so.
They took the perceptual quality of Jans through that autoencoder's discriminator.
Yep.
They took the stability and diversity of diffusion models. They took the control of transformers using cross-attention, and they combined all of it into a system that's efficient enough to run on consumer hardware.
That is the summary. They identified that the pixel was the wrong unit of currency for generation. The latent vector is the right unit.
Let's wrap up with the aha moment. For me, the genius of latent diffusion is that separation of concerns.
Yeah.
You don't need to paint every single pixel from scratch. You can dream in this compressed, abstract space, the latent space, and then you have a separate, dedicated translator, the decoder, to turn that dream into a high-fidelity reality.
I like to think of it like a chef versus a chemist. The diffusion model is the chef. It's the artist.
Yeah.
It decides what ingredients go together to make a delicious meal.
Okay.
The autoencoder is the chemist. It worries about the precise molecular structure of the food. But the chef doesn't need to know chemistry to cook, right? They just need to know what flavors work together.
And by separating those roles.
The chef can work much, much faster.
And the impact of the separation has been huge.
It completely reduced the barrier to entry from tech giant supercomputer down to single GPU. It effectively democratized high-resolution image synthesis.
Yeah.
And that's where we're seeing this incredible explosion of creativity and tools in the open source community right now.
So here's a final provocative thought for you to mull over. We've just spent this whole time talking about how compressing images into latent space lets us generate visuals efficiently.
Right.
We're already seeing similar logic being applied to audio generating music by diffusing spectrograms in a latent space.
Yeah.
What happens when we start applying this latent diffusion logic to video? Or to entire 3D environments?
We are already standing on that precipice.
I mean, if we can dream up a static snapshot on a home computer today, are we moving toward a future where we can generate entire realities? You know, movies, video games, immersive worlds.
All of it.
All optimized to run on the hardware you already own. We're moving from generating snapshots to generating realities.
And the engine under the hood is exactly what we talked about today. It's going to be a wild ride.
It certainly is. I hope this deep dive gave you a solid mental model of how the magic trick actually works. Thanks for listening, and we'll see you in the next deep dive.